Hey guys, 9-1 inverse variations. All right, so we've got 2 or 3 examples that we're doing in this first part, and then we will resume with the continued doing the final examples. All right, excuse me, starting with inverse variations, today we are looking at how to use those, and with that, we need to also talk about direct variation. So back in chapter 2, this was back in September, October, we talked about direct variations. A direct variation is an equation in the form y equals kx, where k cannot equal 0, and k was your constant of variation, and you were given 2 points, had to find the constant of variation, or given the coordinates, so on. Now, an inverse variation is, instead of y equals kx, you have xy equals k, or y equals k divided by x. The x is in the denominator, so that's how we know it's the inverse. All right, again, k cannot equal 0. All right, so k is still a constant of variation, but now instead of it creating a line, it's going to create this sort of graph, right? The exponential, or the inverse graph, sorry, not exponential. And one thing that I want to draw your attention to is this statement here, because this is something that they like to put on the EOC, that sort of language. Notice that as the rate increases, the time decreases. Doubling the rate halves the time. The inverse variation, RT equals 24, or T equals 24R, models this situation. All right, first example. Suppose that x and y vary inversely and x equals 3 when y equals -5. Write the function that models that inverse variation. That's simply a matter of substituting in the values for x and y and solving for k, and then plugging k back into that original equation. So we know the inverse variation is y equals k divided by x, or x times y equals k. So plugging in 3 for x and -5 for y gives us -15, so k is -15. Writing that in the inverse variation form, you have y equals -15 divided by x. Fairly easy, hopefully, textbook easy. So now let's take a look at the one that's going to be for your notes. Suppose that x and y vary inversely, and again, that vary inversely is a key term that tells you that we are going to be using the y equals k over x. And then x equals 7 and y equals 4. Write the function that models the inverse variation. Well, if y equals k divided by x, then again we know that xy equals k. X is 7, y is 4. So then 7 times 4 is 28 equals k. And then we have to write that function that models that inverse variation. So then it's y equals 28 over x. You do not include the 7 and 4 because you were just using that 7 and 4 to find the constant of variation. Okay, pretty easy. The hardest part here is remembering that the inverse variation is y equals k divided by x. All right, example 2, identifying direct and inverse variations. So now, is this relationship direct, inverse, or neither? So you have to find that out by using the y equals k over x, or y equals k times x. The easiest thing here to do is, if you're multiplying the x and y, and they come up with the same value each time in these tables, then you know that's inverse. If you are getting this x, y, multiplying those or dividing those to get the same constant of variation, then that is a direct. So it's a little bit backwards of what you want to think. Let's go ahead and see that in play, and then you'll have your textbook to refer to up here if you want to. All right, so is the relationship between the variables in the table a direct variation, an inverse variation, or neither? Write functions to model the direct and inverse variations. All right, So for the, for the direct, we know that it is y equals kx. For the inverse, we know that it is y equals k divided by x. So to find k here, you would have y divided by x. To find k here, you have xy equals k. So now we need to see what happens when we multiply or divide. Now, for me, multiplication was always easiest. Ooh, sorry. For hall duty tomorrow. So for me, the easiest was always to multiply first, and so that's what we're going to start with. So 2 times 0.7 is 1.4. 4 times 0.35, guess what, is 1.4. 14 times 0.1 is 1.4. So I got each of those. The k is 1.4, and I got that by doing k equals x times y. So the only one that matches that xy is over here, the inverse. So this is an inverse variation, right? And the equation is y equals 14 divided by x. Sorry, this is a little sloppy. I'm kind of sitting funny. All right, now let's take a look at the second one. All right, so we multiplied those, so that's probably not going to work here, but let's give it a go anyway. So negative 2 times 6 is negative 12. Negative 1.3 times 5 is going to give us negative 6.5, so that won't work. So we'll go ahead and erase. All right, so now let's try division. Now remember up here, it's y divided by x. So 6 divided by negative 2 is going to give us negative 3. 5 divided by negative 1.3 is not negative 3. So we can't get a constant of variation by multiplying, and we can't get a constant of variation by dividing, so this one is neither. And if there is no direct or inverse variation, then there is no function that we can model at this stage. All right, the third part, negative 2, 5, 4, negative 10, and 6, negative 15. All right, so multiplying negative 2 times 5 is negative 10, 4 times negative 10 is negative 40, not working. So let's try 5, or the y, divided by x. So 5 over negative 2, negative 10 over 4, and negative 15 over 6. If we simplify those, we still have negative 5 over 2, negative 10 over 4 is negative 5 over 2, and negative 15 over 6 have a like factor of 3, which would leave us with negative 5 over 2. So the constant of variation in this case is negative 5 over 2, and we got that by doing y over x. So that one is a direct variation. So this is a direct variation, and its function is going to be y equals negative 5 over 2 times x. You could write that as negative 5x over 2, but I personally like to keep my constant of variation as a separate factor within that term. So, all right, let's see. Third example and final one from this section. Zoology. Heart rates and lifespans of most mammals are inversely related. Okay, so right there, they are inversely related. We know that this is y equals k over x, or that xy equals k. Use the data to write a function that models this inverse variation. Use your function to estimate the average lifespan of a cat with a heart rate of 126 beats per minute. All right, so we have heart rate and lifespan. It says they are inversely related, so we can multiply those together to get the constant of variation, which is what they have done here in each of these cases. And what they have found is that the constant of variation is about see, is that 1 billion? I believe so. And then to find the average lifespan of a cat, which the lifespan of this cat right here trying to attack me is probably not going to be as long as this one. With a heart rate of 126, you would set it up as 126 times the span equals 1 billion. Divide both sides by 126, and you get 8 million, which is 8 million minutes, or about 15.2 years. All right, so let's do this one. The pressure, this is a physics science type problem, and it says the pressure of a sample of a gas at a constant temperature varies inversely. All right, so there's our key word, varies inversely, as the volume, V. Excuse me. Use the data in the table to write a function that models this inverse variation for the sample of gas. Use your equation to estimate the pressure when the volume is 6. All right, so we can look at all of these, and if we know that the relationship between the pressure varies inversely with the volume, then we know that we can get the constant of variation by multiplying each of these together. So 3 times 32 is 96. 5 times 19.2, so 5 times 19 is 95, plus that 1 is going to be 96, and 8 times 12 is 96. So you can see the constant of variation remains constant. All right, now use your equation to estimate the pressure when the volume is 6. So we have 6 times the pressure equals 96. You divide both sides by 6, and we have that the pressure is 16. And that would be pounds per inches squared. All right, that's it for the first day. Easy stuff, hopefully. The hardest thing, like I said, is remembering that the inverse variation is y equals k divided by x, or xy equals k. And then the direct variation is the other one.